Good evening, everyone. Welcome to my lecture series on A Level Chemistry. Today, I will talk about hydroxyl compounds, looking at the chemistry of alcohol and phenol. So these are the learning outcomes in the A Level syllabus. All right, I will go through every single objective in my lesson. We will also talk about this in general, the nomenclature, the properties of alcohols as well as phenols. We will discuss the acidity of phenol, alcohol, and water, the preparation of alcohol, as well as the reactions involving both alcohols and phenols. And here are the references and the websites. Hydroxyl compounds are compounds that contain the hydroxyl functional group. So hydroxyl compounds can be alcohol or phenol. For alcohol, the OH group was attached to the sp3C carbon of alkyne or substituted alkyne group. As for the phenol, the OH group is directly attached to sp2C carbon of the benzene ring. So these are the examples. Starting with alcohol, this is the general formula, CnH2n plus 1 OH. Alcohol can be classified as either primary, secondary, or tertiary alcohol, depending on the number of alkyne groups attached directly to the carbon bearing the hydroxyl group. So, different classes of alcohol will respond differently to different reactions, in particular, oxidation. Now, so these are the difference between primary, secondary, and tertiary alcohol, which is related to the number of R groups on which the OH is attached to the carbon. So if there's two hydrogen bonded to C and with only one R group bonded to C, it is a primary alcohol. Two R groups, secondary, three R groups, tertiary. So these are the examples of the primary, secondary, and tertiary alcohols, including the phenols as well. Now, what are the physical properties of alcohol? The boiling points of alcohol are much higher than those of alkanes with similar number of electrons or having the same number of carbon. So, for example, both compounds, ethanol and propane, have 26 electrons. The alcohol have a much higher boiling point because it have hydrogen bonding in addition to ID-ID interactions. So because of hydrogen bond formed between molecules, hydrogen bond is a much stronger force of attraction, requiring more energy to overcome. Alcohol has a much higher boiling point. What are the factors that affect boiling point? The length of alkyne chain. So with increased length of alkyne chain, the boiling point increases because there is more energy required to break the stronger ID-ID interactions between the molecules, resulting in a higher boiling point. And this is due to larger and more polarizable electron cloud branching. Branching of the carbon skeleton lowers the boiling point. So with branching, the molecules become more spherical, more compact, resulting in less surface area of contact for ID-ID interactions than in straight chain isomers. So as you can see, 2-methyl propane 1-nol is having more branching, is more spherical, resulting in less surface area for contact. With number of OH groups increases as shown, the boiling point increases because it leads to more extensive hydrogen bonding, and this increases the boiling point of the alcohol. Alcohol are more soluble in water compared to the corresponding alkane because alcohol form hydrogen bond with water. However, with increased length of the hydrogen hydrogen carbon chain, the respective alcohol will have a marked decrease in solubility because the hydrocarbon portion is actually non-polar. So with increased carbon chain, the ID-ID interaction become predominant compared to the hydrogen bond. And also the non-polar hydrocarbon chain also get in the way or interfere with the hydrogen bond between the water molecules and themselves. So the solvation of long chain ROH molecules will entail hydrogen bond breaking between the water molecules, and it's too endothermic a process for the positive entropy change of solution to counter. Now, as you can see, with increased carbon chain, the solubility drop. And these are the reasons as discussed. An increase in number of OH group will increase the polarity of the compound and its solubility in water. So in sucrose molecule, it is a big molecule with 12 carbon atoms. So we will expect it to be relatively non-polar. The presence of 8 OH group will cause the molecule to be non-polar and hence more soluble. In organic solvents, we will expect alcohol to be miscible with most organic solvents, as the hydrocarbon portions can interact with the hydrocarbon portions of other organic solvent via ID-ID interactions. So alcohol can dissolve in water as well as organic solvents. So as a result of having a polar OH group as well as a non-polar hydrocarbon chain, alcohol acts as solvent to dissolve both water-soluble substances and organic substances. Example, using NaCN in ethanol, the CH3CH2 portion of ethanol will interact with the R of alkyl halide, while the OH group of ethanol will interact with the ions to improve miscibility between NaCN and RX. Now, this summarizes the lab preparation of alcohol. We shall look at them individually, starting with hydration of alkenes, which is electrophilic addition. Now, looking at the example of the hydration of ethene to form ethanol, the reagents and conditions are cold concentrated sulfuric acid and water at high temperature. So in step 1, the ethene reacts with the sulfuric acid to form ethyl hydrogen sulfate. This is an example of an electrophilic addition. In step 2, the intermediate product, ethyl hydrogen sulfate, reacts with water in hydrolysis, which involves the breaking or cleavage of bonds, and sulfuric acid is formed back. So sulfuric acid behaves like a catalyst because it's regenerated at the end of step 2 and is used again in step 1. The overall equation is the hydration of ethene to form ethanol. This is what we are familiar with at O level, but these 2 steps is actually the mechanism of the reaction that is actually broken down into 2 steps. So what happened here in step 2 is, okay, the bonds between the O and S is cleaved. Okay, and the O or the H from the water will go to here to form the OH. Okay? The other H will form H2SO4. The other H and O will form H2SO4. So you have the H plus and the OH minus formed with the SO3H. Now, this method of preparation of ethanol is actually unsuitable for lab use due to the high temperature and high pressure required. What are other methods to prepare alcohol? Alkaline hydrolysis of halogenoalkanes with the reagents and conditions as either sodium hydroxide aqueous or potassium hydroxide aqueous with heat. So this is an example of nucleophilic substitution, okay, where the OH substituted the X to form this. Now, if you recall the previous lecture on halogenoalkanes, we discussed on the difference between SN1 and SN2. So for primary alcohol to be formed, SN2 is used. For tertiary alcohol, SN1 is the reaction that produces the tertiary alcohol. Because in SN1 reaction, tertiary alcohol with more carbon donating groups, the alkyl groups attached to the central carbon, okay, will allow a more stable carbocation ion form. Whereas for SN2, it is suitable to produce primary alcohol from primary halogenoalkanes because of less interference from the alkyl group causing the steric interference. Now, other methods include reduction of carboxylic acid, aldehyde, or ketones. So we can use lithium aluminum hydride or sodium boron hydride to provide hydride ions in the reaction. The reaction is carried out in two steps. Number one, lithium hydrogen hydride deliver H minus, hydride is H minus, not H plus, to the carbonyl group. And then there is protonation of the resulting intermediate to form the alcohol. So from carboxylic acid, we can use this lithium hydrogen hydride in dry ether, which is used as the solvent to dissolve the compound or the reagent. Okay, so reduction is the gain of hydrogen, and there is a step two to protonate the mixture, or rather the intermediate, to form the alcohol. So for this carboxylic acid, it will form primary alcohol. Aldehyde can also be reduced to form primary alcohol, and there are also other possible reagent and conditions for the reduction. Ketone is used to form secondary alcohol, okay, using similar conditions and reagents. Now, so these are the equations to represent the reduction reactions. What are the chemical properties of alcohol? So we are going to discuss each of them. Very quickly, combustion, we have learned that in great depth. So with a good supply of air, meaning complete combustion or excess oxygen present, the alcohol will burn with a pure blue or non-luminous flame to give carbon dioxide and water. With a limited supply of air, the alcohol will burn with a yellow or luminous flame, and some soot is also formed. Now, alcohol does react with sodium and other reactive metals in group 1 to form alkoxides and hydrogen gas. So this is an example of a redox reaction. And this reaction involves the cleavage of the OH bond. So the OH bond is cleaved and sodium is added to the molecule with hydrogen release to form hydrogen gas. Now, we have learned this at O level about esterification, where alcohol reacts with carboxylic acid in the presence of acid catalyst, concentrated sulfuric acid at elevated temperature to produce sweet-smelling ester. And this is a reversible reaction, which means it is not fast and it takes a few hours to reach equilibrium. The concentrated sulfuric acid is necessary to supply the H plus to catalyze the reaction. So at the end of the reaction, this sulfuric acid will be regenerated and can be used to catalyze another reaction. Acylation is the introduction of acyl group into a molecule, and the common acylating agent is acyl chloride, which is shown here. And it also yields ester when it's added to alcohol. Since HCl gas is formed, there will be steaming white fumes of HCl evolved. This is not HCl aqueous hydrochloric acid. This is HCl gas. And when the gas comes into contact with the damp blue litmus paper, it will turn red. Note that anhydrous condition must be used because acyl chloride will hydrolyze readily in water. Comparison between esterification and acylation is that acylating agents are actually more reactive than carboxylic acid. For esterification, the reaction cannot be completed, but for acylation, it can be completed. Therefore, the yield of esterification will be lower than acylation, and there will be heating required for esterification, but for acylation, the reaction can be held at room temperature. No catalyst is required for acylation, but esterification, there is a need to have H2SO4 catalyst. Now, for the next reaction, halogenation, which is a type of nucleophilic substitution, it involves the substituting the hydroxyl group with halide, accompanied by the cleavage of the CO bond. So ROH, right, upon reaction with dry halide, okay, in gaseous state, and of course heating is required, it will actually cleave the CO bond to form a new compound, RX, meaning you form a halogenal alkane. So it is the opposite of the reaction we are familiar with, where RS can become ROH. It's possible also. So to produce RCl, we will use dry HCl and zinc chloride and heat. For RBr, we use sodium bromide in concentrated sulfuric acid. But in producing Ri, okay, meaning it's a halide salt with iodine, we will use concentrated phosphoric acid because sulfuric acid is not used, as it will actually oxidize NaI. Okay, well, actually the H2SO4 can be used here because NaBr is not easily oxidized in this case. Now, another way is to use PX3, which can be either PCl3, PBr3. So to produce Ri, we need a rate P with iodine in situ. Okay, Pi3 is actually not stable, so we avoid using that to prepare Rx from ROH. Now, so if we use PCl5 or SOCl2 to convert ROH to RCl, again, HCl is one of the byproduct form. So there will be a steaming white film. And if we want to use PX3, PX5, or SOCl2, we should take note that anhydrous condition must be used as they will react readily in water. So with dry hydrogen halide, ROH and HX, upon heating, it will form RX and H2O. So the dry HX is bubbled into the alcohol and then heated to produce the halogenal alkane under different conditions. So for RCl, okay, we use HCl to produce the RCl. So it can be CH3Cl or CH3CH2Cl. Okay. For RBr, we use HBr to react with the ROH. And the dry HBr must be bubbled into the alcohol and heated to produce the halogenal alkane. The alcohol is heated under reflux with NaBr and concentrated sulfuric acid to generate HBr in situ. For Ri, however, Hi cannot be prepared with concentrated sulfuric acid because it will oxidize iodide to iodine. So we use concentrated H3PO4, which is non-oxidizing. With phosphorus halide, okay, we can actually form the halogenal alkanes as well. All right. So ROH reacting with RX3, X can be any of the halide to form RX and H3PO3. So this is an example. Or we can use phosphorus pentachloride, which produce RCl, POCl3, and HCl. And again, we will observe steaming white film of HCl. We can also use thionyl chloride, SOCl2, to produce these products. And again, we will observe white film of HCl form. The reason why this is actually a preferred method because the byproducts are gases which can be easily removed. So the separation will be easier. Now, and this reaction, as well as the reaction with PCl5 to produce HCl, can be used as chemical tests for aliphatic OH group because we can observe the production of white film and deduce the presence of aliphatic OH groups. Now, when we carry out dehydration of alcohol, it will produce the corresponding alkene. So these are the conditions required for the dehydration process. So the type of reaction is actually elimination. So the mean of the reaction, is hydration, and the type of reaction is elimination. So for reagents and conditions, we can use excess concentrated sulfuric acid at 170 degrees Celsius or pass the alcohol vapor over aluminum oxide at a higher temperature of 350 degrees Celsius. So this diagram shows the laboratory apparatus for the dehydration. Okay, so during the reaction, corn sulfuric acid may actually oxidize some of the alcohol, okay, and is itself reduced to SO2. So it is important to remove the acidic SO2 by bubbling the solution through sodium hydroxide solution. Okay, so that the mixture to be collected will have no SO2 as best as possible. To determine if an organic compound undergoes oxidation or reduction, we concentrate on the carbon atoms of the starting material and product and compare the relative number of CH and the CZ bonds, where Z is an element more electronegative than carbon, like O, N, or halogen. Now, so this X in our notes in this context will refer to halogen, like Cl, Br, and I. Oxidation results in increase in number of CZ bonds and usually CO bonds, or decrease in number of CH bonds. Okay, because during oxidation, oxygen should be added and hydrogen removed. Reduction will be the opposite of oxidation. So if we examine the diagram here, we can see that this molecule of methane should be the most reduced form of carbon because it has 4 CH bonds. Upon oxidation, it will form alcohol with less hydrogen and more oxygen. Okay, the number of hydrogen remains, but the number of oxygen increased by 1. With further oxidation, the alcohol forms a carbonyl compound, in this case, an aldehyde. And further oxidation will produce carboxylic acid, okay, which is methanoic acid in this case, is methanol. So we can see that although the number of oxygen does not increase per molecule, but the number of hydrogen actually decreases by 2. Okay? And then there's increase in oxygen here. And the most oxidized form of carbon will be having all the hydrogen removed, and we only have C double bond O, which is CO2. So the complete oxidation of carboxylic acid will produce CO2, which is the most oxidized form. And the reverse is true. So as we oxidize the organic molecule, we will see an increasing number of CO bonds, and in the case of reduction, an increasing number of CH bonds. The oxidation of alcohol involves the loss of 1 or more hydrogen, alpha hydrogen, from the carbon bearing the OH group. Primary and secondary alcohols are readily oxidized to carbonyl compounds and carboxylic acid. So what is alpha hydrogen? Okay, so alpha hydrogen is the circled hydrogen shown in the diagram. It's the hydrogen on the C bearing the OH group. So you have the C here, and this C, okay, bears the OH group. So alpha hydrogen is the hydrogen that is bonded to the same C that is bonded to the OH, as shown in the diagram. So this H here is not alpha hydrogen. Now, suitable oxidizing agents is potassium manganate or potassium dichromate. So manganate ions can be used in neutral, alkaline, or acidic medium. Whereas for dichromate ion, it functions only in a medium or sulfuric acid. The product of oxidation is governed by the type of alcohol and the power of the oxidizing agent. So oxidation of alcohol can be employed to distinguish between the different classes of alcohol. So for primary alcohols are readily oxidized on heating to aldehyde. Okay, so in the presence of excess oxidizing agent, the reactions proceed further to produce carboxylic acid. So we have the primary alcohol first oxidized by acidified potassium dichromate to form the aldehyde. Upon further oxidation, it will form carboxylic acid. So it is not a direct jump from alcohol to acid. There is an intermediate product between them. So the extent of oxidation will determine the product form. But if you use potassium manganate, okay, it will produce the carboxylic acid directly without forming the aldehyde in the intermediate step. And these are the observations that you should be very familiar with. So in order to isolate the aldehyde form, we must use acidified potassium dichromate as the oxidizing agent and perform immediate distillation from the alcohol, because we want to prevent further oxidation of the aldehyde to form the acid. So we must separate, okay, the aldehyde out quickly to prevent further oxidation of it. So there's a need for immediate distillation. So this is the setup that shows how we can actually produce the aldehyde. Why is it that we can isolate the aldehyde by immediate distillation? Why is distillation a suitable method for the separation? This is because aldehyde actually have lower boiling point compared to alcohol. For example, ethanol, which is an aldehyde, has a boiling point of 20 degrees Celsius, whereas ethanol is 78 degrees Celsius. The aldehyde experience weaker intermolecular forces because aldehyde only have PD-PD interactions. It doesn't have hydrogen bond, unlike alcohol. So if you are able to keep the setup at a suitable temperature between these two boiling points, aldehyde can be distilled off once it is formed. For secondary alcohol, they will be oxidized to ketone, not aldehyde. And the conditions are either potassium dichromate that is acidified and heated, or potassium manganate, acidified and heated as well. For tertiary alcohol, because they have no alpha hydrogen, they cannot be oxidized further. They will just remain unoxidized. Now, if we want to test for alcohol, these are the tests we can carry out. So for the first reaction here, which is called Iodoform Test, is only positive for alcohol that has a methyl group and a hydrogen atom attached to the carbon, at which the hydroxyl group is also attached. So it has to be something like this, a methyl and a hydrogen bonded to the carbon. So when such an alcohol is warmed with iodine and aqueous sodium hydroxide, we will see yellow crystals of the triiodomethane. That's why we need a methyl group, so that we want to see the yellow crystal of CHI3 form. All right. So what happened is that there's a cleavage of bonds here, and the CH3 will form CHI3 with the iodine. Okay. And the other product will be RCOO minus Na, because of presence of sodium hydroxide. But what is observed is this: it will appear as yellow crystals. And here are the reagents and conditions required. For more details on the mechanism, this is what happened. So in the first step, the alcohol is oxidized. All right. So with iodine as the oxidizing agent, in the presence of an alkaline, sodium hydroxide, we have the alcohol losing 2 of its hydrogen, okay, and form this at the start, okay. So the hydrogen will go to the hydroxide to form the water, okay. In the second step is iodination. It occurs in a stepwise manner in which H in CH3 is successively replaced by I. So one by one. So one by one, the hydrogen is replaced by the iodine to form this intermediate product. So the hydrogen again form water with the OH minus. Finally, we have the alkaline hydrolysis, okay, where the bonds between C and C is broken, okay. In order to break this bond, you must use hydrolysis, which is able to break this bond. And you will form CHI3, and the O will form with the C. So this is the yellow crystals observed. So if we combine these three equations together, we will form this balance equation. Now, let's move on to the last part on phenol. So this is the nomenclature where phenol have an OH group attached directly to the benzene ring. Appearance-wise, phenol is colorless, hygroscopic, and a crystalline solid with this melting point. Phenol have relatively high melting point compared to other organic compounds of similar electron cloud size because it forms intermolecular hydrogen bond. The boiling point of substituted phenol depends on the extent of hydrogen bonding. So if we compare 2-nitrophenol with 4-nitrophenol, we observe that in 2-nitrophenol, there is also intramolecular bond. But in 4-nitrophenol, the two OH groups are not near to each other. So they do not form intramolecular hydrogen bonding. So in the case of 2-nitrophenol, due to intramolecular hydrogen bonding, the ability to form hydrogen bond with neighboring molecules will reduce. This results in less extensive intermolecular hydrogen bond and a lower boiling point. Phenol are only partially soluble, unlike alcohol, because it forms hydrogen bond with molecules. However, it has a big non-polar benzene ring, okay, that is actually affecting the extent of hydrogen bond between the phenol and water. So if we want to change the solubility, we can either do it by heating or addition of alkaline. Now, these are the chemical properties of phenol. The difference between phenol and alcohol is that they do not undergo reactions involving the cleavage of the CO bonds due to the partial double bond character of the CO bond. So we will explain why this is so, okay? Now, for the hydroxyl group in phenol, it reacts with acyl halides to form ester. So, unlike alcohol, phenol does not react with carboxylic acid, but it does react with acyl halides to form phenyl ester. Okay, so this Cl cut off, then this is formed, this is cut off to form the HCl. Acylation is effective, right, in NaOH, as the alkaline will first react with phenol to form the phenoxide ion. So there's a reason why if you add sodium hydroxide, the reaction, okay, the acylation will be more effective. Okay, so this one, we're trying to do this one. Okay. The reason why alcohol can react with carboxylic acid but not phenol is because phenol is actually a weaker nucleophile than alcohol. Because the problem with phenol is that the lone pair of electrons on the oxygen atom is delocalized in the benzene ring due to overlapping of the orbitals between the pi electrons orbitals and the pi electron orbitals of the oxygen. And H lah. So for reactions involving benzene ring of phenol, so in the first part, we talk about the hydroxyl part. How does it react? And now we look at the benzene ring. So here we are looking at nucleophilic reaction. Here we are looking at electrophilic addition, substitution. So the hydroxyl group is 2,4 directing, meaning it is bonded to 2 of 4 carbon in the benzene ring. Okay, so hydroxyl group is electron rich. It has a lone pair of electrons, which means that it can be electron donating. So the delocalization of the lone pair of electrons on oxygen into the benzene ring will help to increase the electron density of the ring. So because of this, the phenol undergoes electrophilic substitution much more readily than benzene. And reactions of phenol can be carried out under milder conditions, and we can expect poly substitution to occur. So the first example is halogenation, which is actually electrophilic substitution as a type of reaction. So we can use bromine in aqueous medium. Phenol reacts with bromine at room temperature without Lewis acid catalyst, unlike benzene with aqueous bromine. And a trial substituted product will be formed instead of a mono substituted in the case of benzene. So if we have orange bromine added, it will be decolorized and a white PPT of 2,4,6-tribromophenol will be formed. So this is observed as a white PPT. Okay, so these are the two observations made. The orange Br2 decolorized and the white PPT formed. We can also use bromine in iron fillings, iron 3 halide. This is what we have learned under electrophilic substitution of benzene. Okay, so we can use this to initiate the electrophilic substitution to make the benzene react. But in the case of phenol, we can just use bromine in CCl4, which is an organic solvent for bromine, as bromine dissolves better in organic solvent as it's a non-polar molecule. So the phenol will react with Br2 that is dissolved in CCl4 to form either 2 or 4 bromophenol. Okay, remember we mentioned that the hydroxyl group will be 2,4 directing. So it will lead to bromine attaching itself to the second carbon, to see the first carbon, second, third, fourth, which means the OH group causes the benzene to 2,4 directing. So we will observe the orange red Br2 decolorize. Now, when aqueous bromine is used, we see poly substitution. But how come with CCl4, we will see mono substitution? This is because, right, phenol oxidizes partially in polar solvent. So with aqueous bromine added, there's water. So it will form phenoxide ion in water. And then the aromatic ring in the phenoxide ion is actually more electron rich because of that. Because the OH minus, okay, the electrons there can be can move to the delocalized ring to make it more electron rich and more susceptible to more electrophilic substitution and form poly substituted products. The next reaction is nitration, which is also a type of electrophilic substitution. So the phenol will react with concentrated or dilute nitric acid at room temperature without using concentrated sulfuric acid. So with concentrated nitric acid, we will see trial substituted products, 2,4,6-trinitrophenol. With dilute nitric acid, mono substituted product obtained. Okay, so the concentration has an impact on the type of product that could be formed. So since the OH group is an electron donating group, it will be 2,4 directing. Okay. So for nitration of benzene, just recall what we learned in electrophilic substitution. A nitrating mixture containing concentrated sulfuric acid and nitric acid are actually carefully mixed and added to the benzene. Then this mixture is refluxed on the water bath between 55 to 60 degrees Celsius. Now, if we want to distinguish phenol, we can use FeCl3, which is the most common test to confirm the presence of phenol. Okay, so phenol will actually react with aqueous iron 3 chloride to form a violet complex as shown. So this is a complex with 6 of the phenoxide ion bonded to Fe. Okay, so this is phenoxide. So this is 3 plus. This is 3. Each one is minus, so there are 6 of them. So 6 times -1, -6. So you have 3 minus 6 to give you -3, which explains why the overall charge of this complex is 3 minus. Okay, because this is a phenoxide ion actually. Now, so this reaction is used to test for presence of phenol. Okay, so there are of course other tests for phenol, like use of aqueous bromine or use of aqueous sodium hydroxide, where you observe that the phenol actually dissolves in aqueous sodium hydroxide. Now, let's recall the basic of acidity. Okay, a Bronston-Lowry base is a proton acceptor. A Bronston-Lowry acid is a proton donor. So the larger the Ka, the stronger the acid. The smaller the pKa, the stronger the acid. And this is how we represent the equation, okay, to calculate for the concentration of the species using Ka. Now, if you look at the data here, we can see that ethanol has the lowest Ka value, which means that it is the weakest acid among the three. So to evaluate the acidity of this compound, okay, we will need to deprotonate it by removing the hydrogen and assess how stable this conjugate base is. So this is the acid, okay, where it donates the proton. So proton donated, okay, meaning the proton leave the acid, and the product is a conjugate base. In this case, a alkoxide ion, okay, O minus. Now, let's look at this word example. You can pause the video first to check your answer later. So in this question, explain if you would expect an aqueous solution of alcohol to turn damp root litmus paper red. Now, we know that alcohol should have lower acidity than water. So an aqueous solution of ethanol is actually neutral and should not turn litmus paper red. Now, this is the reason to support the oxidation. We have the electron donating alkyne group. So they are electron donating, means that they will cause an increase in the electron density on the oxygen atom in the alkoxide ion, RO minus. This will intensify the negative charge. So because of the electron donating group alkyne, the negative charge is intensified. And when this negative charge is intensified, it will actually destabilize the alkoxide ion and make it more ready to accept proton. Now, the equilibrium position in one lies less to the right, indicating that your alcohol is actually a weaker acid than water. Equation 2 shows the dissociation of water. Okay, so the alcohol does not dissociate in water to give a significant high concentration of H plus ion. So it's not enough to turn the litmus paper from blue to red. Not enough. Because the alkoxide ion will quickly gain proton and you have very little of it formed. So this is the comparison of acidity between alcohol, various alcohol and water. So primary, secondary, tertiary. And from the table, we observe something. Okay, the difference is the number of electron donating groups. So the more electron donating groups of the alkyl group present, the more intensified the negative charge on O, and it make it more destabilized, and hence it doesn't really remain as RO minus. So it will actually lower the acidity of the alcohol. Now, meaning that this alkoxide ion will actually react with the hydrogen and form back more of this. So you have less of these two, more of this. So it will be less, more. So water compare. Water actually mostly is molecule, but compared to ROH, it will be less, more. So alcohol is even a worse Bronsted Lowry acid than water itself. But from this table, we can observe a few things. The more electron donating groups it has, and the less acidic, and this increases the pKa value. Now, alcohol is a weak acid, so it can only react with reactive metal in a redox reaction to form to form hydrogen gas. But it does not react with carbonate or hydroxide. Okay, and also note that the Ka of carbonic acid is higher than the Ka of ethanol. As for phenol, it's different. It actually behaves well as an acid as it donates its proton. So phenol is even more acidic than alcohol, and it can turn litmus paper red. Now, why is it so? First of all, we have to understand that the p orbitals of the oxygen atom overlap with the pi electron cloud of benzene. So there is a good overlapping between these two orbitals. And this will result in the negative charge of oxygen destabilized, meaning there is dispersal of negative charge over the ring. So the phenoxide ion is said to be resonance stabilized, where equilibrium position lies towards the right. So if we have this stabilized, okay, because of the overlapping of orbitals, because of the delocalization of the negative charge, because of the dispersal of negative charge, so it means that you have more of this. And therefore, there's sufficient H plus to turn litmus paper red. Now, so it is slightly different from alcohol. So for phenol, definitely, even at room temperature, it can react with the reactive metal, sodium, to form the phenoxide ions. Okay, and with sodium hydroxide, it can also react. But if you recall, for alcohol, it cannot react. But phenol is able to do it. It has enough H plus to react with the OH minus in the acid-base reactions. However, with sodium carbonate cannot at room temperature. Same for sodium hydrogen carbonate as well. Again, the carbonic acid, because you see, you are talking about this one. So because Ka of carbonic acid is higher than K of phenol, okay, so it is not possible for phenol to react with sodium carbonate. So there will be no reaction and hence no effervescence of CO2. All right, so you can actually use this test to distinguish between the three classes of organic compounds. So this is a summary For alcohol, sodium metal, okay. This one, not okay. This one, not okay. But for carboxylic acid, all okay. Phenol, not okay with sodium carbonate because of this reason. The Ka of carbonic acid is still higher than Ka of phenol. So, not likely for it to happen. Okay. Now, so comparing to OH minus, the alkoxide ion RO minus is actually more unstable because of the electron donating effect, as we mentioned. So compared to OH minus, the phenol ion is more stable due to resonance stabilization. And we have already talked about this earlier. So in other words, for the conjugate base, right, we have to conclude that the phenol, this one, phenol ion, have a higher stability compared to hydroxide. And of course, our RO minus will be even, alkoxide will be even worse in terms of stability. Now, so this is the relative stability, relative acidity of the three substances. Okay, let's look at the effect of the substituents on the acid strength of phenol. So we have observed that when there is electron withdrawing groups like this, all this, they actually increases the acid strength of phenol. So the electron withdrawing group, right? Okay, they are present on the phenol ring to further disperse the negative charge. All right, so it will help to further stabilize the phenoxide ion. If you have electron donating groups in the ring, it will decrease the acid strength of phenol. Okay. The electron donating group will intensify the negative charge on oxygen atom. Thus, it will destabilize the phenoxide ion, make it more prompt for reaction, prompt to reaction. So electron withdrawing group increase the acid strength. Electron donating group decrease the acid strength. Okay. So finally, this is a summary on the difference between alcohol and phenol. Okay, very quickly, what we have covered in the last 1 hour. I hope this lesson benefit you. Hope you have a better understanding on the difference between ethanol, phenol, okay, and the chemistry of them all. Okay, so that's it for today. Thank you.